Hello. In this video, we'll discuss the energy changes that take place during a bungee jump. So this is the bungee jumper of mass M. He jumps and screams, of course. The bungee rope straightens out after he has fallen through a distance of L. And he reached the minimum height after falling through an additional distance of X. Obviously, during the jump, we have energy conversions among GPE, elastic PE, and KE. And we're going to sketch the variations on this graph here. Some important landmarks. So this is the topmost position. This is when the bungee rope has just begun to stretch. And this is when the bungee jumper reached the lowest position. If we take the lowest position to be our reference point for GPE, then the GPE graph will start from 0 and increase linearly until it reaches some maximum GPE value at the topmost position. It's a straight line graph because the GPE varies linearly with distance. Between this point and this point of the motion, all the loss in GPE is going to the gain in KE. So the KE graph will also be a straight line graph from the point when the guy jumped until the point when the bungee rope begins to stretch. The elastic potential energy will remain at 0 until the bungee rope starts to stretch. At the lowest point, the bungee jumper will be stationary and therefore its KE is 0. This means that all the GPE at the beginning of the jump should be converted into nothing else but elastic potential energy at the lowest point of the jump. So we know that elastic PE started at 0, remains at 0 until the bungee rope starts to stretch, and at the lowest point, the EPE stored is exactly equals to the GPE at the beginning of the jump. But the elastic potential energy will not increase linearly from 0 to this value here. In fact, if the bungee rope obeys Hooke's law, then we know that it should be a quadratic graph joining these 2 points together. In fact, if we halve the extension, then the EPE should become 1/4. So the EP is 0 until the rope starts to stretch, and it's a quadratic curve here. When we half the extension, the EP becomes 1/4. Now we can complete the sketch of the KE graph. Notice that the KE graph reaches 0 at the lowest position, and that it reaches a maximum value somewhere in between these 2 positions. At this position, the tension in the bungee rope is still smaller than mg. In fact, it's 0 at the beginning of the stretch. So the net force acting on the jumper is still downward, so this guy is still speeding up. So the KE is still on the rise. It's only when the rope is sufficiently stretched such that the tension in the rope matches the downward weight that the bungee jumper experiences a net force of 0 and starts to slow down. That's why the maximum KE is not reached here when the net force acting on the jumper is still downward mg, but here when the rope is sufficiently stretched such that the tension in the rope matches the downward weight. Beyond this point is when the tension is larger than the weight, is when the bungee jumper starts to experience an upward net force, and that's when the jumper starts to slow down. Okay, so GPE is a straight line graph, EP is a quadratic graph, and the KE is straight line for the first part and a quadratic for the second part. Think it through yourself and see if it makes sense. Alright, ta-ta!